Greetings everyone, this is Mr. Mull. Today I'm doing a podcast on ionization energy and successive ionization energies. So we're going to go ahead and get started here today. First off, let's define ionization energy. Ionization energy is the amount of energy that's required to remove or pluck away the outermost or most loosely held electron from 1 mole of isolated neutral atoms in a gaseous state to infinity. So if I have a mole of sodium atoms and I input some energy, or I add enough energy, we'll call it IE1. IE1 stands for that first electron I want to remove. So if I add some amount of energy, in this case 496 kilojoules, if I add that much energy, I'll be able to take away electrons from a mole of sodium atoms. We input the energy. I'm going to pluck out my little electrons, remove them to infinity. And we're left with sodium plus 1, and we've turned it into an ion, hence the name ionization energy. So we would call that IE1. That would be our first electron that we removed. If I wanted to come in and go and take another electron away from this positive ion, we would call that IE2. If I wanted to remove a third electron, we call that IE3, and so on and so forth. So now that we know what ionization energy is, and what these little symbols mean, IE1, IE2, IE3, we're going to look at what actually happens to this amount of energy as I continue to remove electrons. So let's look at a magnesium atom. So I'm looking at this Bohr model of the atom, and I'm seeing my electron configuration. In that first energy level, we have our 2 electrons. In the second energy level, I have my 8 electrons, and then in that third energy level, I have my 2. So ionization energy says the amount of energy needed to remove the outermost electrons. So I'm going to look at those outermost electrons, and I'm going to pick one of them, and we're going to talk about IE1, the first electron to remove. So if I want to pluck this away, it's going to cost some energy. For magnesium, it is 736 kilojoules. Okay, 736. So it's going to take me 736 kilojoules to remove a mole of those electrons from a mole of magnesium atoms. So if I look at my electron configuration, I would be plucking away one of these electrons, and we would be left with 3s1. So I'm going to remove an electron. Now we're left with an ion, magnesium plus 1. I've lost an electron. I still have 12 protons. But now I have 11 electrons, so now I have that positive charge. So 1s2, 2s2, 2p6, 3s1. So now, if I wanted to keep going with this, I'm looking at my proton to electron ratio, and I'm noticing that if I want to go and take another electron, we'll call this IE2, that now I've kind of lost a kid from the playground, and there's still the same number of recess A's, or protons, that charge, that effective charge to the nucleus, has actually gone up. The pulling power of my magnesium plus 1, or my effective nuclear charge, has actually gone up now. So it's going to be a little bit more difficult, or a little bit harder, to pull away another electron. Okay, so I've got rid of this first electron. Okay, that one's gone. So if I want to remove another one, let's look up here. What I'm going to do is, if I want to pluck this away, I have to put some energy in there. We'll call that IE2. And when I input that energy, I could find this on a table or something. It's 1445 kilojoules. So it definitely is more energy, because I'm fighting that kind of more positive. It's still the same amount of positive, but the effective nuclear charge has gone up now. There's more protons to electrons. So my value goes up. Now if I wanted to keep going with this, magnesium, remember, really does want a full energy level. So I've already lost 2. Instead of gaining 6, I'm losing electrons, like metals like to do. If I lose another one, it's still going to cost more energy, but I want to empty out that shell. So if I take this last electron, we're going to lose that there, and it's going to turn to 0. So now I have magnesium plus 2. Okay, 1s2, 2s2, and then 3s is 0. It's empty now. So now I have magnesium plus 2. And I'm going to go ahead and draw on here that now that I've removed those outermost electrons, the third energy level has just kind of been emptied out. Okay, there's nothing left out there. So if I wanted to come in again and 2s2, 2p6. If I wanted to come again and take another electron, well, it only has 10 left. Okay, so now we're at 12 protons and 10 electrons. Well, now my effective nuclear charge has even gone up more. Okay, effective nuclear charge has gone up way more. So that's going to make it more difficult to pluck away one of these little electrons in the second energy level. But there's an even more important reason why this third ionization energy to pluck away one of these is going to be even greater. Look at what's happening to the shells. I've just emptied out the third energy level. But now I'm trying to break into magnesium's full shell. And magnesium is finally good. And now to break into this inner energy level, or this core electron, there's going to be a big jump. So I'm going to look up this value, and it's around 7,000. It's 7,730 kilojoules. Oh, it's almost seven times bigger, or 7 times more energy to remove an electron from that inner shell. Okay, so there's really that large jump when I start breaking into those core electrons, or those inner shells. Okay, and we'll summarize all this stuff in a little bit. Okay, another example that I want you to look at, and this is the one that we just did, is looking at those that when we break into that core electrons, there's that gigantic jump. When we break into those core electrons, so those inner shielding electrons. Okay, let's go ahead and move to the next one. Looking at potassium, I want you to predict for me now which ionization energy, i.e. question mark, for potassium is going to be the big jump. The big jump. So let's start with potassium. I'm going to go ahead and look up potassium is 19. So looking on the periodic table, 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Okay, so this is the electron configuration for potassium. So right now potassium has 19 protons, 19 electrons. So IE1, this is IE1, we're going to take away one of these little electrons, and that's going to do what with that fourth energy level? Remove the electron from it. So now it's empty. So my K plus 1, IE1 is equal to 418 kilojoules per mole. And then if I want to go in and pluck another electron, well, once that's gone, well, now I'm going to start breaking into this third energy level, which is full. So to take one of these electrons, IE2, that's going to be my big jump. That's going to be the big jump, IE2. Okay, to break into my core electrons, it gets way bigger. For potassium, it's 3,018 kilojoules per mole. So now we're not only breaking into an inner energy level, those energy levels are closer to the nucleus, so all those electrons are kind of being kept a little tighter to the nucleus, but also we're breaking into a full shell. So they're closer, we're breaking into a full shell, double whammy, we get this gigantic jump. Let's look at one more example just to make sure you've got this. Let's look at aluminum. Okay, so if I look at aluminum's electron configuration, 1s2, 2s2, 2p6, 3s1, 3p1, 3s2. Okay, aluminum is number 13 on the periodic table, so it's into the p block just a little bit. So looking at aluminum, if I want to start plucking electrons off of aluminum, here's my ionization energy. This is kind of a nice little graphic here. Here's IE1. Let's put it up here. IE2, IE3. Looking at my values here, I can see that IE3 is definitely the biggest. But why? Let's look at the electron configuration. Okay, so looking at the P1, the first electron. Okay, so let's look at this guy here. If I want to remove this electron, the first and outermost energy level electron, it's going to take some energy, but it's going to be relatively low. So the first one's going to be a little bit lower. Once I break into the next electron, I want to remove one of these. It's still the same energy level. I haven't broken into any new shells. But now I have a little bit more energy because, remember, aluminum had 13 protons and 13 electrons. But as this number of electrons goes down, my effective nuclear charge goes up. So it's going to keep getting bigger and bigger. So I'm going to remove one of these, i.e. 2. Okay, that would change that to 1. And then if I want to remove the third electron, it's going to take a little bit more energy, 2,000. So we're kind of going up. It's kind of a gradual increase. But what happens is that when I clear out this outermost shell, remember aluminum wants to get to 8. It has 3. So it could lose 3 or gain 5. Well, it's going to lose those 3, and when it does that, and I want to come in for IE4, what do you think is going to happen to the amount of energy needed? It's going to go way up. Okay, so that fourth one is around 11,600. So when I break into those core electrons, remember, not only am I fighting the more positive nucleus as I remove electrons, so those are pulling everything in tighter and closer, making it harder to pull away electrons, but also you're trying to break into a new shell. Okay, so you're going to see those big jumps. So to kind of summarize, I would probably write this down, that each successive removal requires more energy. Remember, we're fighting, we're fighting that increased in effective nuclear charge. And then we get those large jumps when a core electron is removed. Okay. And then last but not least, I have a picture here. This is just showing kind of a cool table. You could pause this and kind of look at this. But this is just showing where those big jumps are. And if you look at the periodic table and kind of notice where those jumps are, you'll see that all these big numbers are corresponding to electrons being removed from like a fresh energy level or a fresh full shell. This is just a little bonus. Looking at here, as I keep removing electrons, you see this little guy trying to pull away an electron. As I'm fighting to pull away these electrons, I'm fighting that bigger charge from the nucleus, and that obviously is going to take more energy. This would be, we've already removed 3 electrons, so this would actually be IE4, trying to pluck away the fourth one, okay, because we already had to remove 3. IE4 would be quite a lot of energy. But looking over here, I'm trying to pull an electron away. I've already lost 10. This would be IE11. Notice how close those electrons are now to the atom as the atom has gotten smaller and smaller. So very, very difficult to remove those electrons. Well, this wraps up successive ionization energies, and I hope that this was helpful.